Now starting a new chapter, probability. So in this chapter, the first topic is random experiment. Random experiment. Now what means random experiment? As for example, if we toss a coin, then before tossing a coin, we want to toss only one time. So before tossing a coin, we can say possible outcomes in advance. There are only two possible outcomes, either head appears or tail appears. So possible outcomes that we can say in advance, but exactly which will occur, that can be seen after performing experiment. So every such experiment is said to be random experiment. So first definition is random experiment. An experiment is called random experiment if it satisfies following two conditions. It has more than one possible outcome. When we toss a coin, there are two possible outcomes. If we toss a die, balanced die, there are six possible outcomes. Either one or two or three, there are six outcomes when a die is tossed. So it has more than one possible outcomes. Second condition is, it is not possible to predict the outcome in advance. We can't say which will come exactly after performing experiment in advance. So such experiments are random experiments. Then next word, outcome. Outcome means possible results. A possible result of a random experiment, that is outcome. And the sample space, set of all possible outcomes of random experiment, that is said to be sample space. When a coin is tossed once, then sample space contains only two outcomes, H and T. If a die is tossed once, sample space contains six outcomes, like that. So you already work on this topic of probability in 10th class. Now more about probability in 11th class. Now to understand this experiment and possible outcomes, more examples. Describe the sample space for the indicated experiment. Here experiments are indicated. Let us write down sample space. A coin is tossed 3 times. So sample space S is, sample space we denote by S. It is denoted as S. In short, sample space, first letter S. So sample space when coin is tossed 3 times. When a coin is tossed 3 times, possible outcomes are head appears, again head, 3 times head, then 2 times head, H, first H appears, then tail appears, then H appears, then T, H. So say, look, 3 times H, then 2 times H, Now one time H, that is HTT, THT, TTH. One time H means 2 times T. Now 0 times H, that is all times T. Tail, tail, tail. So these are possible outcomes when a coin is tossed 3 times. 1, 2, 3, 4, 5, 6, 7, 8. If you toss a coin 3 times, possible outcomes 2 raised to 3. If you toss only 1 time, there are only 2 possible outcomes, H and T. So 2 outcomes. So toss 1 time, outcomes 2 raised to 1. If you toss 2 times, outcomes 2 square, 4 outcomes. If you toss 3 times, number of outcomes 2 raised to 3, that is 8 outcomes. If you toss 4 times, a coin is tossed 4 times, so number of outcomes 2 raised to 4, that is 16. So remember simple formula to check number of outcomes if a coin is tossed n times. A coin is tossed n times or n coins are tossed at a time. Outcomes are same. 2 raised to n. Number of outcomes 2 raised to n. So here coin is tossed 4 times. So number of outcomes 2 raised to 4, that is 16. Let us put list of these 16 outcomes. See, method is first outcome H. Now with H, put all these outcomes. See, H is fixed in first place. Now second, third, fourth place, we join these all outcomes. So H, then H, 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 H. Then with H, 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 T. Then again with H, H, T, H. Again with H, T, H, H. Then with H, H, T, T. With H, T, H, T. With H, T, T, H. With H, T, T, T. So see, these 8 outcomes are joined with H. These outcomes are followed by H. Now what we do, this H I replace by T. First H I am replacing by T, then again repeating same procedure. T, H, 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 comma, T, H, H, T, comma, T, H, T, H, comma, T, T, H, H, comma, T, H, T, T, comma, T, T, H, T, comma, T, 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 H, T, 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 T. So these are 16 outcomes when a coin is tossed 4 times. If a coin is tossed 5 times, number of outcomes 2 raised to 5. If coin is tossed 6 times, number of outcomes 2 raised to 6. Like this. Now in this question, 2 boys and 2 girls are in room X. Say in room X, there are 2 boys. Let me denote these 2 boys by G1, G2. 2 girls boys we denote by B1, B2, and girls we denote by G1, G2. 1 boy and 3 girls in room Y. In room Y, 1 boy and 3 girls. Here 1 boy, so that boy we denote by B3. B1, B2, B3. Three girls. Here already we labeled name G1, G2. So here three girls are G3, G4, G5. Specify the sample space for the experiment in which a room is selected. See, experiment is select a room and then a person. Select a room, then a person from that room. So here possible outcome sample space is select a room, then a person from that room. So suppose here there are two rooms, X and Y. So when we select a room, X can be selected or Y can be selected. Suppose we select X. X is selected. Now select a person. So with X we select B1. X, B1. With X we select B2. From X select B2. From X select G1. From X select G2. So these are possibilities if room X is selected and a person from that room. Now second possibility, if Y is selected, room Y is selected, then select a person, only one person. So from Y select B3. From Y select G3. From Y select G4. From Y select G5. So these are possible outcomes associated with this experiment. So this is sample space for this experiment. A box contains one red and three identical white balls. One red ball and three identical white balls. Two balls are drawn at random in succession without replacement. Write the sample space for this experiment. See here, sample space is two balls. Two balls are drawn at random in succession without replacement. Means take a ball, note down its color, then don't put it back. Without putting back means without replacement, take another ball. So here one red ball and three white balls, so total there are four balls. If first red ball is selected, first selected ball is red, then don't put it back. Then when you select second ball, so it comes from these three identical white balls, so second ball will be white. If performing this experiment, if first ball comes from these three white balls, first ball is white, second ball can be red. First ball white, second ball can be red. So here word is in succession, means one by one. So first red, second white, first white, second red. Experiment is not like that take two balls together in your hand. Take one by one in succession. Third possibility, first ball is white and second ball is also from these three white balls, so second is also white. So these are three possibilities. Only one red ball. So both the times red is not possible. So sample space associated with this experiment contains these three outcomes. Now with this question, an experiment consists of tossing a coin and then throwing it second time. If head occurs, say here first of all, toss a coin. Tossing a coin, when we toss a coin, then either edge appears or tail appears. So tossing a coin and then after tossing a coin, then throwing it the second time if head occurs. If head occurs, then toss a coin again. So again, toss again. Toss a coin again. If tail occurs on the first toss, then a die is rolled. A die is rolled. Find sample space. So here sample space is coin is tossed. In the first toss, H appears. If H occurs, then second time toss again a coin. So when second time tossing coin again, second time H can appear, second time T can appear. So H T. If head occurs in first toss, second time toss a coin again. So second time H can appear, T can appear. In first toss, if T appears, first toss, if T appears, then toss a die. So when you toss a die, in second outcome, in second result, on second toss, we can get 1 from die. This is outcome from die. T, here 2 can appear. With T, here 3 can appear. Similarly, T4, T5, T6. So these are possible outcomes. Here experiment is a coin is tossed. Coin is tossed. So there are two possibilities, either H appears or T appears. If outcome is head, a die is thrown. That means throw a die. If die shows up an even number here, if it shows even number, then the die is thrown again. So when tossing a die second time, again there are two possibilities. Here even can appear, odd number can appear. If even number appears, then a die is thrown again. Throw die again. See, once again, repeating procedure. A coin is tossed. When a coin is tossed, then either H appears or T appears. If the outcome is head, a die is thrown, then throw a die. Now when a die is thrown, if even number appears, then the die is thrown again. It means if odd number appears, don't do anything, because we are asked to do further. If even number appears, then throw die again. But if odd number appears, don't do anything. And here we are asked to perform this procedure when tossing a coin H appears. If T appears, don't do anything. Experiment is over. So here if T appears, experiment is over. Here in this section, odd number appears, experiment is over. So sample space is when H appears. If H appears, then throw a die. If even number appears with H, if 2 appears, then suppose here I put 2. H, if 2 appears, then throw a die. So if 2 appears and then throwing a die, we can get 1, we can get 2, we can get 3, 4, 5, 6. First toss H, second toss if 2 is obtained, then throw a die. So when throwing a die again, 1 can appear, 2 can appear, 3 can appear, 4 can appear, 5 can appear, 6 can appear. Similarly with H, if throwing a die even appears, means 4 appears. With H 4 appears, or with H 6 appears, then throw a die again. So H4 1, H4 2, H4 3, H4 5, H4 6. 1 2 3, here 4 is missed. 4 5 6, and H, then throwing a die. If even 6 is appeared, then again throw a die, because 6 is even. So H6 1, H6 2, H6 3, H6 4, H6 5, H6 6. So if first outcome is H, second outcome from die is E1, then throw a die third time. So third time any number from 1 to 6 can appear. But tossing a coin, if a tail appears, then we are not asked to do, this procedure is missed. When odd number appears, continuing this, here with H, throwing a die, if odd appears, means if here 1 is odd, 1 appears, or 3 appears with H, if 3 appears, or with H, if 5 appears, 1 3 5, H and odd appears, so H1 H3 H5, then don't do anything next. So here in first toss H appears, second toss odd appears, experiment is over. Now if first outcome is tail, T, then here don't do anything. So no question of second outcome or second and third outcome, so here experiment is over. So this is the sample space associated with this experiment. Now, in this question, a die is thrown repeatedly until a 6 comes up. What is the sample space for this experiment? Experiment is that toss a die. Whenever you get a 6, stop the procedure. Experiment is over. On the first toss, if a 6 appears, then experiment is over. If on second toss 6 is obtained, experiment is over. It may be possible that whenever you toss a die, in first 99 tosses, no 6 appears. Then on 100th toss, 6 appears. Then stop the procedure. So, bunch of these 100 numbers in which last digit is 6, it is also a possible outcome. So let us put here all possible outcomes. Toss a die. On first toss 6 appears, experiment is over. Now, if on first toss 6 is not appeared, suppose on first toss 1 appears, first toss 2 appears, first toss 3 appears, first toss 4 appears, first toss 5 appears. Then toss second time a die. Second time 6 appears, experiment is over. Second time 6 appears, experiment is over. With 3, then 6, over. First is 4, second is 6, over. First is 5, second is 6, over. If first is 6, second 6, this is not allowed. Because on the first toss, if you obtain 6, then experiment is over. Don't toss again. And so this outcome already included as the first outcome. So this is the procedure. Now, if on the first toss 1 appears, second toss 1 appears, then toss again. If on the first toss 1 appears, second toss 2 appears, then toss next. If on the 1 appears, 3 appears, then toss again. If 1, 4, toss again. 1, 5, toss again. If 1, 1 is obtained and then 6 appears, experiment is over. 1, 2, then third toss 6 appears, experiment is over. 1, 3, 6, over. 1, 4, 6, over. 1, 5, 6, over. Then 1, 6, 6 not allowed. Because as 6 obtains, don't toss again. And already this outcome here be included. So this is the procedure. Now, on the first toss, see these are the observations in which first place we have taken 1. Now I am taking 2, 1, 2, 2, 2, 3, 2, 4, 2, 5. Then don't take 2, 6 because 2, 6 experiment is over. Then 3, 1, 3, 2, 3, 3, 3, 4. Sorry. Leave space for 6. 3, 1, 3, 2, 3, 3, 3, 4, 3, 5. Then don't put 3, 6 because at 6 experiment will be over. Then 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 6, 1, sorry, 5, 1, 5, 2, 5 3, 5 4, leave space for 6. This is the trick if we don't want to miss any outcome. So here 5 2, 5 3, 5 4, 5 5. Then don't start triplet by 6, because if 6 is obtained on first toss, then procedure is over, already included. Now here I put 6 6 6 6. Everywhere in third place, third outcome, I am putting 6. Now, in first 3 toss, if 1 1 1 is obtained, then 6 is obtained. Procedure is over. If suppose 1 1 2, then 6 obtained. Procedure is over. If suppose 1 1 3, then 6, procedure is over. So this can be continued. This sample space contains infinite elements. One of the possible outcome in this sample space, it can be like this also. Suppose 1 2 1 3 4 5 1 3 4 5 5 3 1 4 5 5 3, and then 6 appears. Then experiment is over. So group of or bunch of such digits can appear as an outcome. So outcome contain 1 digit, 2 digits, 3 digits, 4 digits, 40 digits, like this. So this outcome, this sample space contains infinite many elements. So sample space is the set of all outcomes. Sample space is the set of all possible outcomes of random experiment. Now next topic is event. Now see here, there are some words in this topic of probability which are similar to which we learn words in the set theory, sets and operations. So same algebra which was from set algebra. See, the first word is event. Any subset E of a sample space S is called an event. Any subset of sample space is event. As for example, suppose in this space I am explaining example. Toss a die. Toss a die once. Sample space associated with this experiment is set of these 6 outputs. This is sample space. Now here I put its subsets. E1. E1 is a subset. Suppose I am putting 3, 6. E2 is 1, 3, 5. E3 is 2, 4, 6. These are subsets of S. So these are events. These are events. Every subset of S is said to be event. Now see, when we toss a die, suppose 6 appears. Toss a die if outcome is 6. If 6 appears, then what we say? So 6 is in this event. 6 is also in this event. So what we say? E1 occurs and E3 occurs. E1 occurs, E3 occurs. Suppose 5 appears. Toss a coin, and if 5 appears, now 5 is in this E2. So what we say? E2 occurs. Meaning of occurrence of event, when we say that this event occurs, it means whatever is output, if output is contained in that event, check whether obtained output belongs to which event, then we say that event occurs. So look here words. The event E of a sample space S is said to have occurred if the outcome W of the experiment is such that W belongs to E. This is outcome from this sample space. This is outcome from this sample space. Any outcome from sample space, check whether it belongs to, in which set, in which event. This belongs to E1 and E3. So what we say? E1 and E3 occur. 5 appears in 5. 5 appears in E2. So E2 occurs. If W does not belong to E, then we say that event E has not occurred. When we toss a coin, if 5 appears, then tossing a coin, if 5 is appeared, then what we say? E2 occurs. E1 doesn't occur. E3 does not occur because 5 does not belong to E1 and E3. So this is the meaning of occurrence of events. Now, null set is subset of S. S itself is subset of S. And we know that any subset E of a sample space S is called an event. So because these are subsets of S, these are also events. Null set is said to be impossible event, and S itself is said to be sure event. Whole sample space S is called sure event. Simple event. If an event E has only one sample point of a sample space, it is called a simple event. In short, singleton set. Suppose if I put here set containing 1 or 3 or 2, E5, 6, these are singleton set. These are subsets of S. This is subset of S, this is subset of S. So these are events. But these events are containing only one sample point. So these are said to be simple event. These are simple events. In set operations, we had word singleton set. So this is similar to that word singleton set. Here we use word simple event. Then next word is compound event. If an event has more than one sample point, it is called compound event. This is compound event. This event has more than one sample points. This is compound event. This is compound event. Event containing more than one elements. Here for element we are using word sample point. See, these are sample points. 1 is sample point, 2 is sample point, 3 is sample point. Sample point means outcome. Every outcome word sample point is used. Complementary event. Set of all sample points which are in S. but not in A is said to be complementary event to A. It is also called event not A, denoted by A dash. Suppose here for this experiment, this is sample space. A is event containing 2, 4, 6. Now I put here outcomes which are in S but not in A. So see, 1 is in S but not in A. 3 is in S but not in A. 5 is in S but not in A. So these are sample points which are in S but not in A. So this event is said to be not A. It is not A. Not A notation is A dash. It is complementary to event A or complement of A, complement event. So what is similar to complement of a set? In set operation we had word complementary, complement of set. Similarly here complement of event. Event A or B. If we take union of two events, then it is said to be event A or B. If you take intersection, for intersection we use word AND. Event A and B means A intersection B. Event A but not B. A but not B means not denoted by A minus B or A intersection B dash. Means elements which are in A but not in B. So words are same which we learn in set operations. A minus B means in A but not in B. A intersection B dash means in A but not in B. Mutually exclusive events. Mutually exclusive events. Suppose here E1 is 1, 3, 5. E2 is 2, 4. Now look these two events. Their intersection is empty. If intersection is empty, then events are said to be mutually exclusive events. So these are mutually exclusive events. For events A and B, if intersection is empty, then they are said to be mutually exclusive events. In set operations, we had word disjoint sets. So here this is, we can say, substitute for disjoint sets. Instead of disjoint sets, mutually exclusive events. Then if union of two events is S, then A and B are exhaustive events. If you take here union of E1 and E2, so union is not S because 6 is nowhere in these two sets while 6 is in S. So here E1 union E2 is not equal to S. So these are not exhaustive events. But if I keep here word 6, element 6, then union of these two is S. So in this case, these are exhaustive events. So mutually exclusive means intersection empty. Exhaustive means their union is S. So this terminology was like a terminology of set theory, nothing new. An experiment involves rolling a pair of dice and recording the numbers that come up. Describe the following events. Event A, the sum is greater than 8. B is 2 occurs on either die. Event C, the sum is at least 7 and a multiple of 3. Which pair of these events are mutually exclusive? So here, first of all, sample space associated with experiment of rolling a pair of dice and recording the numbers that come up is S is equal to rolling a pair of dice and recording the numbers that come up, that is ordered pairs 1 1, 1 2, 1 3 up to, this is up to 6 6. In short, this can be written as xy, where x is x and y are from these numbers. X and y are natural numbers from 1 to 6. So this set can also be expressed in short by this method. So total there are 36 elements. S contains 36 elements. Now here, first of all, event A. A is the event that it is event that the sum is greater than 8. So from these 36 outcomes, we are taking those in which sum is greater than 8. Sum is greater than 8. So in this first line, last element is 1 6, where sum is 7, not greater than 8. From second line, last element is 2 6, whose sum is 8. But we want greater than 8. So no any element from second line. In third line, up to 3 5, sum is 8. But after 3 5, element is 3 6. Here sum is 9, which is greater than 8. So this is the last element of third line. From fourth line, up to 4 4, sum is 8. Next is 4 5. 4 6, then from line of a 5 5 4, 5 5, 5 6, then from last line 6 3, 6 4, 6 5, 6 6. See, these are the elements in which sum is greater than 8. Keep remember that no any outcome or sample point should be missed. So 3 6, 4 5, 4 6, 5 4, 5 5, 5 6, 6 3, 6 4, 6 5, 6 6. Sum is 9 or more than 9. Event B. 2 occurs on either die. 2 occurs on either die in the first line, 1 2. 2 is on second place. Now in second line, 2 1, 2 2, 2 3, 2 4, 2 5, 2 6. 2 occur on either die, that means at least one time 2 appears. Then in third line, only one element, 3 2, fourth line 4 2, fifth line 5 2, sixth line 6 2. So 2 occur on either die. Then C is event in which the sum is at least 7 and both conditions must be satisfied. That is meaning of this word and. Sum is at least 7 and a multiple of 3. Sum is at least 7. Now see, 7 is not multiple of 3. 8 is not multiple of 3. 9 is a multiple of 3. 10 is not. 11 is not. 12 is multiple of 3. So here sum is at least 7 and a multiple of 3. That means we are taking those elements in which sum is multiple of 3, that is, and more than 7, that is there are two numbers 9 and 12. Sum is 9 or 12. So sum 9 or 12, that is in the line of 3 6, here sum is 9, that is multiple of 3. Sum is multiple of 3 and this is more than 7. So 3 6 4 5 4 5 5 4, here sum is 9. 6 3, here sum is 9. So 3 in the line of 3 3 6, then line of 4 4 5 5 4 6 3 and 6 6, here sum is 12. So these are the elements whose sum is 9 or 12. If sum is 9 or 12, that means sum is at least 7 and multiple of 3. So condition for C is satisfied. So these are required events. A, B, C are required events. Now, which pair of these events are mutually exclusive? Mutually exclusive, that intersection is empty. So check whether intersection empty in which two events. Say here, this is common. So intersection is not empty. So these are not mutually exclusive events. Check in B and C. In B and C, see here, nowhere there is 2 and here everywhere there is 2. So nothing is common in B and C. Here B intersection C is empty. Check A and B. In A and B, here everywhere there is 2. Here nowhere 2. There is no 2 anywhere. So therefore A intersection B is also empty. So not only B intersection C, A intersection B I am putting first and B intersection C is also empty. Not A intersection C empty. Therefore A and B are mutually exclusive events, as well as B and C are also mutually exclusive events. There are two pair of mutually exclusive events. So which pair of these events are mutually exclusive? So there are two pair of events mutually exclusive, A and B, B and C. Now let us discuss more for this example. Suppose we want event not A, event not A. We describe event not A. Not A, that means this is also denoted as A dash. Event not A, that means elements which are in S but not in A. So we take those elements from S which are not in A. So see 1 1 is there. 1 is in S but not in A. Then 1 2, 1 3, 1 4, 1 5, 1 6. This line of 1, it is in S but not in A. Now take from second line 2 1, 2 2, 2 3, 2 4, 2 5, 2 6. These are in S but not in A. Now from third line, say 3 6 is there. So 3 1, 3 2, 3 3, 3 4, up to 3 5. These elements are in S but not in A. Then 3 6 is there. So don't include in A. Don't include in A dash. Then line of 4. So here there are 4 5, 4 6. So which are not there? 4 1, 4 2, 4 3, 4 4. Then 4 5, 4 6 are there. Then 5 4. So here 5 1, put 5 1, 5 2, 5 3, 5 4 is there, so don't include here. 5 5, 5 6 are there, so don't include here. Then 6 1. 6 1 is in S but not in A. 6 1, 6 2. So these are elements which are not in A but in S. So they are in not A. Event not A means A dash. So this is complement to event A. And union of A and A dash, it must be S. Total must be 36. See 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. So total 36. No one is missed. So this is not A. If we want event not A, B and not A, B and not A, that means it is B minus A, B minus A, B and not A. So B minus A, that means we can also put this as B intersection A dash, means elements which are in B but not in A. Elements which are in B but not in A, that means they are in B and in A dash. This is not A. B not A. Here changing symbol to avoid confusion, because dash we are using for complement. So this is A and here it is A dash. Clear? This is not dash. This is A. B and not A means B minus A means B intersection A dash. So we take intersection of B and A dash. B intersection A dash. So this is B, this is A dash. Intersection means check common. So which are common? So 1 2, 1 2 is common. 2 1, 2 1 is also common, 2 1 common, 2 2 is also common, 2 2 is common, 2 3 it is also common, 2 4 is also common, 2 5 is common, 2 6 is common. So these are common. Then 3 1 not common, 3 2 is common. Then 4 2 is common, 4 2 is common. Then 5 2 is common, 6 2 is also common. You can see that B is subset of A dash. All the elements of B are in A dash. You can check this underline. See, all the elements are in this set. So their intersection is B. So intersection is set containing 1 2, 2 1, 2 2, 2 3, 2 4, 2 5, 2 6, 3 2, 4 2, 5 2, 6 2. So this is B and not A, means B minus A. That is, take intersection of B and A dash. This was B, this was A dash. B means 2 occurs on either die, and A dash is not A. That means accept these elements.